following result, that we prepare the system, we prepare a detector, we do a weak measurement, we write down the results, the detector readouts in this weak measurement, then we do a projective measurement of a different observable, and we only keep those results of weak measurements that yielded the result of a specific eigenvalue of the second observable measure. And if we average those results, this subset of the measurement results we've collected, the average of those results is lambda times the real part of this thing we call weak value for some reason. If this was classical system, what would it mean? It means that I measured my spin, and then I did something else, and then I collected a subset of the measurement results. I collect a subset of measurement results, so this subset represents some particular states of my spin. So it is natural to think that this weak value in some way characterizes my spin. However, quantum mechanics is not realistic in the sense that I have some spin state. It does not mean that my spin value is determined. And this is what we see here, that we prepared the system in some state. We post-selected it in a different state. And the average of the post-selected results is not the expectation value of spin. In fact, it can even be outside of the spin spectrum. Indeed, let's take a look. I have this B node times psi I. If this B node times psi I is small, and the matrix element of A is constant, then zeta goes to infinity, can become arbitrarily large. And let me give you one example. Suppose before I give you the example, let me introduce a slightly different notation. You see, it's the same thing, but I called psi I the initial state, and B node, I called it F, final state. So, as people say, we prepare or pre-select our system in state I, we post-select it in state F, and the result of weak measurement yields us weak value provided within the post-selection. So let me take spin 1/2. Let me take the initial state to be up. Let me take the final state to be cosine theta over 2 up plus sine theta over 2 down. And let me take my observable I measure to be sigma x. Then I can calculate that f times I is cosine theta over 2. The matrix element of A flips it to down. So the matrix element is sine theta over component, and thus the weak value is equal to 1/2 tangent theta over 2. Especially for Chris, when I write tangent STG, same as tangent like this. Now, if I take theta be pi minus epsilon, this becomes 1/2 cotangent, and this is the same as cotangent. Pi minus 2 epsilon, and it becomes cotangent epsilon, which, when epsilon goes to 0, is equal to 1 over 2 epsilon. So we see that if I post-select my state to a nearly orthogonal one than the initial state, I can make this expectation value arbitrarily large as I want. I have spin 1/2. The eigenvalues of this operator are plus minus 1/2. This matrix element can be whatever I want. It can be 100, as in the classic article that introduced this. It can be 1,000, it can be a million. There is nothing surprising about it, because, look, what we had is some probability distribution of our detector states. Then we say we do post-selection. What does post-selection mean? We choose a subset of the data. We choose subset of the data. For example, it may happen that we choose this part of the probability distribution. And our eigenvalues are here, but the detector tells us this, because we chose this part of the data. And the average is, therefore, beyond the eigenvalue spectrum. It's not surprising if you think about it like this. But if you try to think about it as the objective property of spin, it's completely surprising and misleading. One more thing I'd like to emphasize is that to get this thing, we need to average over many experiments. We do many experiments in which we do weak measurement, and we do post-selection, and we average over those results, and only then we get this weak value. Therefore, I think it would be more appropriate to call it the weak expectation, or weak expectation value. If you want to shorten it, weak expectation, because it emphasizes that it's the average, it's not the result of a single measurement. But the work was done before I was born, so I didn't have a chance to influence the terminology. It's called weak value. And now I'm going to tell you where it is useful. Because, okay, fine, it's fun, it's something unusual. We can measure something we weren't able to measure easily with strong measurements. But what is it useful for? We're going to look into that now. Before we do that, let me state several results. So this is the average Q. And it gives us the real part of the weak value. And you may ask, what about the imaginary part? Is it unobservable? And the statement is, if you calculate the average P, you get lambda over sigma squared imaginary part of zeta. So you can measure the imaginary part. You simply have to measure the detector's momentum and not the coordinate afterwards. Another comment I'd like to make is what is the actual expansion parameter? I wrote this as O of lambda squared. I said my coupling between the system and detector is small. But you know from, say, doing perturbation theory in quantum mechanics that you expand in some parameter, but actually should be some dimensionless parameter that determines the expansion, that controls the expansion. And the dimensionless parameter is not lambda. In fact, it's lambda over sigma. So this is lambda times lambda over sigma. Which means that the coupling only determines how large the detector shift is. But the fact that when you divide by the coupling, you get the weak value is accurate as long as the shift is much smaller than the detector state width. Same here. The next orders will be suppressed as lambda and sigma, as lambda over sigma, and the reason is that the next orders, we expanded this exponentially. You remember. So the next orders will contain P. P acts as a derivative onto the Gaussian. It acts as a derivative onto the Gaussian. It drops down Q divided by sigma squared. It drops down sigmas. Okay, and the last comment I wanted to make is about the errors. This is the average over many experiments, and I want to be able to estimate how accurately I measured it. I made a number of measurements. I made, say, n measurements, and I want to estimate. I calculated this average experimentally. How close is it to the actual weak value I'm supposed to get? Again, and again, it's controlled by the variance. variance is equal to sigma square over 2 plus some corrections in lambda square over. Say here, what's the variance of our P measurement? It's going to be 1/2 sigma squared plus corrections of lambda squared something. Probably so if we did n measurements, what is the error in our estimate of the average Q? I did n measurements. Out of them, I post-selected some number of n prime, which is the probability that the strong measurement gave me the result I want times the number of measurements. So my error is equal to the square root of average delta Q squared divided by n prime. Which means that by my post-selection, I can achieve huge values of the weak value, but I also amplify the error. When f times I scalar product is small, the error is also large.
Then we need to invite n strip for describe our new error. We invite n strip to describe the new error.
Yes, we say that we do n measurements. I do n experimental runs. I want to measure something about my system. I do n experimental runs. Then I have two options. I can say I can perform two types of experiments. I can say I just do weak measurement, and I average whatever results I have, and then I get n measurements and the error estimate we had previously. Or I can say, I do post-selection. I want to get the weak value. For some reason, I want to go for weak value, which implies that I do some post-selection, which implies that out of my n experimental runs, only n prime give me the data points I use for calculating the answer. Which means that when I calculate the standard error, I should use n prime. And because of this, your error is more or less the same it would be without post-selection, but divided by this post-selection amplitude. Okay, it should be absolute average. So the weak value is amplified by this fi. If fi scalar product is close to 0, the weak value can be huge. Also, the error will be huge because you lose data points. Okay, so that's all we can say about weak values in the standard way, in the general way. Now let's, as I promised, let's look at some application. So after all, weak value can give us something huge. Let's try to use it. Let's try to use it for something. While I'm erasing the board, think what it can be used for. Okay, I'm giving you a hint, which I'm not sure how useful it is. The next chapter is called Value Amplification, which means that we're going to amplify something. We're going to say something is too small to measure it. And using weak values, we will be able to amplify it so that we can measure it. What can it be? I'll tell you about an experiment. It's actually a very old experiment, about almost 30 years old. But it's a nice one. So let me draw its scheme. It's an optics experiment. Have a source of light. Then I have a polarizer, which polarizes my beam at angle alpha to the vertical. It's a linear polarization, angle alpha to the vertical. And I'm going to put another polarizer that will polarize it at angle beta. And I'm going to have a camera and a detector. Of the position. So this is going to be my pre-selection. This gives me the initial state. This is going to be my post-selection. This gives me the final state. And I want to measure something in between. These guys measured, I'll tell you in a moment. Suppose I have a birefringent crystal. What does birefringent crystal mean? It means that its refraction index is different for different polarizations. So that I have some n parallel for vertical polarization and n perpendicular for horizontal polarization. So my crystal is at some angle theta to the light propagation direction. I send a beam of light. It has both polarizations. After passing this polarizer, they are coherent, but I have both polarizations. Now, one polarization is refracted at one angle. The other polarization is refracted at a different angle. So this is vertical, this is horizontal polarization. And they go here. And the vertical and the horizontal polarizations arrive at my camera at different coordinates, and this distance between them tells me about the difference between the two refraction indices. Nice way of measuring this difference, maybe not the best one, maybe interference or something like that would be better, but a valid way of measuring this. Now suppose that I know that my crystal is birefringent. I know that it has some difference between the two diffraction indices. But I don't know what the difference is exactly. What I do know is that the difference is tiny, tiny, tiny. Say a micron. And I may not have a detector that resolves microns. Say if my pixel is 10 microns, I have very little chance of resolving a micron shift. And that's where the weak values come in. This shift would be there without all these polarizers. But these polarizers allow us to do the pre-selection and the post-selection, and that will give us weak values. Let me tell you first how this looks in the optics language. In the optics language, I set a beam, that has a diagonal polarization. So I choose my alpha to be pi over 4. And the beam has some spatial distribution. There's a Gaussian profile. And it propagates. Then it passes through a birefringent crystal. And after the birefringent crystal, let me keep it general. After passing through the birefringent crystal, the two polarizations are shifted in y direction by different amounts. So I get into the minus x squared over w squared. Here I get cosine alpha ex e to the minus y minus a vertical squared over w squared. Do I want 2 here? No, I don't. Plus sine alpha ey e to the minus y minus ah squared over w squared. So one was shifted by AV, the other was shifted by AH, and that's it. In fact, not. In fact, the fact that there are two refraction indices means there is a difference in optical paths. So there will be some phase difference. This phase difference is also proportional to the parallel line of central integral. And then after my beam of light passes through the second polarizer, its electric field looks like this. So the second polarizer, let me check the expression. Yes. So all the second polarizer did, it cut out some component from here and some component from here, which reduced the amplitude. But most importantly, now what was two different polarizations is one polarization. My system, my light is in some polarization state. And I have two components, one that was shifted by something and one that was shifted by something else. And I can calculate the intensity of x, y, which is this. It's going to be some base intensity times cosine square alpha cosine square beta e to minus 2 y minus b square w square plus sine alpha sine beta square e to minus 2 minus ah squared w squared minus 2 cosine plus 2 cosine phi cosine alpha cosine beta sine alpha sine beta e to minus y minus ah squared quite a complicated expression for the intensity. What does it give me? So I can measure the intensity, and what I want to extract is this delta A, which is, how do I define it? AH minus AV, which is proportional to delta N, which is N horizontal minus N vertical. So it makes sense for me to calculate the average position of y of my beam. the average beam position. Say I'll do it at x equals 0. The calculation like this. What it yields is A horizontal plus minus delta A over 2 tangent epsilon plus 1, and I put alpha pi over 4, beta to 3 pi over 4 plus epsilon. And there will be directions of delta n squared, but I'm not interested. So you see that if I choose the incoming polarization at pi over 4, and I choose outgoing polarization at 3 pi over 4, so without the birefringent crystal, I would see nothing. The intensity would be 0. I see that in my center of the beam at the camera, the detector, the effect of the birefringent crystal gets hugely amplified by this cotangent epsilon. And the reason is I cut out everything that wouldn't be there without the birefringent crystal. I cut out everything I'm not interested in. I'm interested in the birefringent crystal effect. So I cut out everything that is not there without it, and what is there because of the birefringent crystal got amplified hugely. Now let's translate this. This is an optical experiment. You may object, okay, this is optics. Optics is classical. What's quantum about it? You can think about it as photons incoming one by one, and then they are pre-selected. Only photons that have the polarization measured in the correct state are let through, so they are post-selected. And the number of photons that pass through is the number of measurements. So the fact that it's classical is like the large number of measurements in our quantum detector model. So let's try to translate this experiment into our von Neumann model and understand what it actually amplifies, why it amplifies it, and what do we actually gain? Do we gain anything by amplifying it? Or what is the nature of the advantage we gain? So if you allow me, I'll erase these two boards. So first of all, we had a Gaussian beam. So it makes sense to identify it with our detector state, which is this. With sigma being this beam width W. Then we measure polarizations. We measure polarizations, and it looks like it's a spin, and it's our system. We apply pre-selection and post-selection on the polarization, so it's our system. So we say that our initial state is equal to say up. The final state is cosine theta over 2 up plus sine theta over 2 down, and theta is going to be pi minus 2 epsilon. Now, what does the birefringent crystal do? It distinguishes between two polarizations, between horizontal and vertical. But our incoming beam was not in the horizontal and not in the vertical. It was at 45 degrees, was between them. It was an equal superposition of horizontal and vertical accretion. Which means that it makes sense to choose the measured observable as sigma x, because the incoming beam is an equal superposition of two eigenstates of sigma x. And then what I know, I measure the average detector position, which is lambda times which is lambda over 2 times cotangent epsilon. And when epsilon is small, this expression will coincide with the expression we got for the optical system. So what do we amplify and what do we measure? You remember what we were interested to measure is this delta A, which stood before the cotangent. So it seems that what we want to measure is this lambda. Okay, since we have the analogy, now let's try once more to understand what's the advantage we gain. We have a detector. We have a fixed detector initial state. We can prepare it only with a given sigma. We cannot prepare it narrower. We cannot prepare it wider. We have it. We are free to choose any pre-selection and post-selection state, whatever we want. We may not do post-selection at all if we wish. We have the interaction between the system and detector. Given. The birefringent is given to us. We know what it does to the two polarizations. So this is given. This is what we choose. This is given. And what we want to measure is this interaction strength lambda. And now we have two very nice ways, two ways we know to measure it, and we can compare their efficiency. One way is we prepare whatever initial state we want. We let the system interact with the detector, and then we measure the detector. And so this is weak value protocol. This is the protocol with no post-selection. And what we will get is that Q is equal to lambda, the excitation value of A. And since A is 1/2 sigma x, it's 1/2 sigma x, not sigma x, as I wrote. This is bounded by lambda over 2. We cannot get anything beyond the interaction strength times the maximum eigenvalue. Here in this weak value protocol that we prepare the system in this state, we post-select it to this state. We get the same lambda over 2 amplified by tangent epsilon. So it seems like, okay, we've amplified this Q. Does it give us any fundamental advantage? Does it allow us to increase the signal-to-noise ratio? Because here, we're going to have the noise. And here we're going to have the noise. The dispersion of Q squared. So it looks like, yes, we have gained the value, but we didn't increase the noise. But don't forget that here, if we do n measurements, we get n data points. And here, if we do n measurements, we get n prime data points that are f times I squared n, which is epsilon squared n. So here we get the accuracy of square root of sigma divided by n. And here we get the accuracy of square root of sigma squared divided by 2 epsilon squared n. So this is 1 over epsilon square root of sigma squared over 2n. So if I want to calculate the signal-to-noise ratio, I want to divide the signal, the average I wanted to measure, to the noise, to my uncertainty in the measured value. here is lambda divided by sigma over the n over 2. And here it's lambda divided by sigma square root of n over 2, cotangent epsilon times epsilon cotangent epsilon, which is less or equal than lambda divided by sigma square root of n over 2. So once more, we did not gain anything in the signal-to-noise ratio, in the relative error. We amplified the expectation value, but we also amplified the signal to the noise, so that the signal-to-noise ratio stayed about the same. So this weak value protocol, despite it amplified the expectation value, it does not give us any fundamental advantage in the signal-to-noise ratio. What kind of advantage does it give them? It gives a sort of engineering advantage. How do we measure these average Q square, and so on? After whatever procedure we do, we are going to get some probability distribution of Q, and this is going to be some shifted Gaussian. Now suppose my detector has some finite sensitivity to finite space resolution. I have to bend my coordinates into some bends. My detector only counts how many photons arrive in this interval. This is my pixel. How many photons arrive in this interval, and so on. Obviously, if my interval is much larger than the shift, I'm going to have the hard time telling whether my Gaussian is shifted at all. And it will be hard to tell for me by how much it is shifted. If instead my bends are small compared to the Gaussian shift, I will easily determine its shift up to the accuracy of my bin, up to the size of my bin. Which means that these two protocols have a practical difference. If this lambda is very, very small, I may not have the resolution to identify this shift. But when I use the weak value protocol, I amplify the shift by a lot, so that the shift becomes larger than my pixel size. I keep the same signal-to-noise ratio. Statistical error is the same. Relative statistical error is the same. But previously, I did not have the engineering ability to measure the lambdas this small. And now I do. And that's the use of weak value amplification. I'd like to pause at this point and ask you about any questions. I have one question. Does it heat? Does it produce heat? Okay. that's good. Any questions? So we see that these weak values, they are not just a gimmick, they are not just some interesting fundamental exercise, but they are also a practical tool that can be used. As any practical tool, you have to know when to use it and when not to use it, when it does help and when it doesn't. But they can be useful. In the last half an hour I have, I'd like to tell you another example of the use of weak values, but not the practical one, not about saying, okay, I can amplify something, I'm able to measure something I wouldn't be able otherwise. This example is how weak measurements and weak values can inspire some calculus identities. This chapter is called Super Oscillations. What do you remember about the Fourier transform? It's linear. Good. Suppose I have some function x, f of x, rather capital F of x, and I want to represent it for x between 0 and L. Then what I can do is I can say I have an expansion with some coefficients of this function. This is the Fourier expansion, and it represents the function accurately, it converges uniformly, it's linear, all sorts of nice properties. And it can represent any function f of x of this interval, any sufficiently nice function. Say it's continuous, should be representable like this. In particular, it could represent function f of x into the I alpha x, with alpha being absolutely anything. Now, I'm going to challenge you and myself. I'm going to say, okay, J is bounded by something, by some number. And my alpha, so I want to represent this function as sum over j from minus lambda to lambda j to the I 2pi j x. And my alpha is going to be larger than 2pi lambda over alpha. Maybe even much larger. I will ask you, is it possible? Is it possible to represent this function like this?
CG will be almost constant.
Why would it be almost constant?
Because for this function CG is 1 over alpha minus PG.
So you're saying that if I will apply the standard way of calculating CJ,
Yes.
that I integrate this function with the complex conjugate of this one over the interval, I can calculate what CJ's are and I can try to represent it with those CJ. Great, and I know it's not going to work for a simple reason. It is representable like that with those CJ in this form, when J is unbounded. And most of the weight will be at the oscillation rates close to this alpha. And here I did not change the coefficients, but I dropped those major contributions. Which means that I know that this sum will not represent this thing accurately. Because I dropped something important. I don't know, and I think this most likely will not be possible. And I'll try to convince you. That
It's known that Fourier series is неравномерно сбивчивый.
it's not uniformly converging. No, it's uniformly converging.
Неравномерно. It means that we cannot take only part of series and expect that it will go to the expected point at any.
That's when the function you're representing is not continuous. When it's continuous, it's fine.
Could we take a look at the original function? I mean, f large at the first line.
F large?
First line. Up.
What do you mean?
Yeah, here, right. So,
I mean, this is this function. And okay. I know that I can represent it like this. Probably I cannot represent it like this.
We have a property of original function.
Yes.
F on both ends of intervals. It's equal.
No, not necessarily. Alpha may
from first formula, it follows.
Yeah, that's why I put this curly brackets. I don't want to get points.
But it's a game of how far are we from both ends.
Yes.
It's a kind of property that original function should be close enough. Not exactly close, but close enough.
I don't care about the ends of the interval. Say epsilon and L minus epsilon is good for you. I don't want to talk about the points where my function is discontinuous or where the series are discontinuous. I want to talk about the nice points inside this interval. What I want to try and convince you that I can represent this function by such an integral. So compared to this formula, I did not increase my cutoff. The maximum frequency I have is well below the oscillation rate. But what I allow myself is I allow all frequencies within that range. Not a discrete set, but all frequencies within that range.
Then,
looks incredible.
Then we could go for a sort of approximation quality And quality
Yes,
would be
yes.
some kind of integral characteristic of both functions, of difference of both functions.
Yes, so we could subtract, absolutely, we can do estimation here.
Okay.
But for now, I'm at least trying to convince you that in the limit, the correct limit, this is exactly this. I may try to say, okay, now I discretize this integral into some sort of a sum, and maybe even with smaller steps, and smaller steps, and smaller steps, and how accurate is the approximation depending on the step size and frequency? I could ask that question. I'm not going to. The article I took it from, they do it for some class of functions. But even in principle, saying that I have only frequencies which are small and reproducing a large oscillation seems completely incredible. Yet, it's possible. And the reason I believe it's possible is the following. Remember that we had this expression we calculated at the weak value for. We said, okay, with some cheating, but we said that approximately it's equal to this. Now this is something large. This is going to be my alpha. And this, if I say that I is equal to sum over A, CA, A, and F is equal to sum over A, C tilde A, then this is equal to this. So this looks very much like this sum. The spectrum of A is bounded. This looks very much like my function, which is quickly oscillating, that I want to approximate. And okay, this we derived with some cheating, but we checked that the expectation of Q and the expectation of P of the detector is exactly what we expect from this formula. So maybe there is some truth to that. In fact, we argued that the formula becomes exact when lambda over sigma goes to 0. However, this is a problem, because when lambda goes to 0, if I take literally the limit of lambda going to 0, this becomes small. This goes to 0, I'm not approximating any really quickly oscillating function. When I take sigma going to infinity, then my Gaussian sitting here on which I'm acting is almost a uniform function. It's an eigenstate of P with the eigenvalue 0. I'm not doing anything non-trivial to it. So this kind of gives me inspiration, but I cannot really argue that it works exactly in any limit. So I want to invent some generalization of this in which I would be able to take a limit where this identity would become exact. And the way to do it is to say that, okay, I have the initial state, which is product of many systems in the initial state. I have, if previously I measured a spin, now I have n spins. And all of them are going to be prepared in the same state. And the final state is going to be these n spins in the same final state. And my system detector coupling is going to be lambda over n, sum over n from 1 to n, a n times p. So essentially what I'm telling you is that I'm going to measure n spins, n systems with one detector. Then I can keep the detector shift while setting the interaction strength to 0 because I increase the number of systems. What does this identity become then? So I have f to the minus I lambda a e I which is approximately equal to f1 minus I lambda a d I, which is approximately equal to, which is equal to f1 I 1 power n. Essentially, the scalar product of these is the scalar product of the initial final state of one spin taken to power n. And here, I have only one of the spins acted upon. So I have here 1 minus lambda divided by n times n f a I 1 f1 1 p, which is approximately equal to e to the minus I lambda f a I 1 1 1 f I 1 1 p times f I 1 1 power n. And the corrections to this are controlled by the coupling strength, which is lambda by n, over the detector state sigma. So when the number of systems I measure goes to infinity, I expect the corrections to this to vanish. On the other hand, this is simply equal to e to the minus I lambda divided by n a1 p f1 I1 to power n. And since n is large, I can expand it, and this simply becomes 1 minus I lambda over n f a I power n. Now the fact that this taken to power n is equal to this when n goes to infinity, I don't need weak measurements for that. That's more or less the definition of an exponential. But without weak measurements, I wouldn't arrive to this identity. And if I use a particular example when A is a spin operator, so it has two eigenvalues, and I can do better, I can put here cosine lambda n minus sine lambda n. This identity is still valid, and the cosines, the sines, they don't matter when it goes to infinity. But this tells me one thing, essentially. It tells me that if I have this. And this, you can view it as 1 plus alpha over 2 into the I x divided by n plus 1 minus alpha over 2 minus I x divided by n power n. But you can use the binomial expansion of this expression. And this is equal to sum over k from 0 to n. 0 and k binomial coefficients to the power minus n. 1 plus alpha power k. 1 minus alpha power n minus k to the I x divided by n to k minus n. So, as promised, I represent this function as a sum of kind of Fourier series. When n goes to infinity, the step of the Fourier series becomes small, goes to 0, but all the frequencies, they are between minus 1 and 1. And yet they represent an oscillation with any alpha. Then what you can prove is that this does not converge uniformly on minus infinity to minus infinity. This does not converge uniformly on real numbers. But if you choose any finite interval, it does converge uniformly. So this is a nice representation of this function. And if you remember that, you see we had some p, we could apply this not just to numbers, we could replace x with an operator p. Then we know that cosine of what does it go? Cosine of p over m plus I p over n plus I alpha sine p over n power n is equal to I alpha p. Now, if we apply this to some function phi q, or let me do psi of x, then I can write the psi of x naught plus alpha is equal to sum over j and is equal to n c of n by j power minus n 1 plus alpha over j 1 minus alpha over n minus j psi of x naught plus j minus m divided by n. So what does it tell us? I have my function. On the right hand side, I have my function evaluated at points from x naught minus 1 to x naught plus 1. And I can get the function value at any point x naught plus alpha with any alpha. That's a formula for extrapolation. Now remember, it becomes exact when n goes to infinity. So I use all the values of the function of this interval. And this is kind of not a surprise. I know that if I have an analytic function, I know its values on some interval, I can uniquely determine the function everywhere. But this is an explicit formula. A good question, of course, a good question would be, suppose I truncate the order, I take some finite n. How good is my approximation? And it's not equally good for all functions. The article I've put on Mendeley in the folder Super Oscillations, they do investigate the quality of this approximation, and they prove that for the functions that decay sufficiently fast at infinity, it's quite good. Okay. But what I wanted to convey is that you wouldn't think this is possible, you wouldn't think this is possible. Doesn't look natural at all. But if you play with weak measurements, you notice some identity, you try to make it exact, you try to do something, and you couldn't. That's an example of something that happens not too rarely in physics, that you prove something completely unrelated while playing with your physical system. That's a nice lesson, I think. With this, I thank you that you came today. Any questions?
We wrote down the binom Newton.
Yes.
The binom Newton is
Yes. This is good. Newtonian expansion. This is binomial coefficients.
And from that we got what we wrote down on the left. Yes.
So we say that we take this thing, we expand it, we take the limit of n going to infinity. You calculate the limit carefully, you get this exponential. On the other hand, this is the binomial, and this is this expansion, and this is kind of the Fourier-like series we wanted. Okay, if that's it, then thank you and hope to see you on Wednesday.